Welcome friends to my YouTube channel. Now yesterday's lecture I have told about mass of earth and mean density of earth and also the mass of sun. Okay, and there I also told the various factors that can affect G. Okay, so let us now see how different factors can affect G, or you can say on which factors the acceleration due to gravity depends upon. Okay, so let's proceed. We have first told that acceleration due to gravity at first depends upon the altitude or height. Okay, so how? Suppose this is earth. Okay, suppose this is earth, this is the center of earth. Okay, and this is the radius of earth, say capital R. Okay, now at first assume that an object of mass m is located at a height equal to the radius of earth. Okay, that means on the surface of earth. Okay, so if capital M is the mass of earth and capital R is the radius of earth, okay, and small m is the mass of the object, then at the surface what will be the acceleration due to gravity at the surface? Previously we saw it, that is gm by r square. Okay, so this is the acceleration due to gravity at the surface. Okay, now let us assume that instead of surface the object located at a height h. Okay, so this is r and this is the height h. Okay, so in this case the object lies at a height h from earth's surface. Okay, so in that particular case, in this case, g will be not g will change. Okay, so at a height r plus h from the center, or more generally you can say at a height h from earth's surface, suppose the acceleration due to gravity we write gh. So what will be it? Gm by r plus h whole square. Okay, so this we can write. Now if we divide these two expressions, then what would be the result? Okay, let's see. If we divide these two expressions, then what will be my gh upon g? It's simply r square by r plus h whole square. That means r square plus 2rh plus h square. Okay, now divide this by r square. So what we get? 1 by 1 plus 2h by r plus h square by r square. Okay, now we have to use an approximation that the radius r is very much greater than the height h. Obviously this is true. So under these circumstances, what we write? This expression becomes this 1 by 1 plus 2h by r. Okay, so this we can simply write as 1 plus 2h by r to the power minus 1, and by using binomial expansion we can write it 1 minus 2h by r, and there we ignore the high order terms, that is x square, x cube. These terms are neglected, so only take the first order term. Okay, 1 plus x to the power minus 1. Okay, we use this formula 1 plus x to the power minus 1. This is simply 1 minus x plus x square dot dot dot, and there we ignore the high order terms, only take the first term. Okay, so from which we can easily conclude that gh, this can be written as g into 1 minus 2h upon r. Okay, so this is the variation of g with height, or you can say with altitude. This is the formula. Okay, so this is the variation of acceleration due to gravity with height. This is a simple expression. Okay, so this is the first case. Okay, now let us move to another issue. Now the second thing, that the next thing that can affect G is the depth. Okay, next thing that can affect the G is depth. Okay, that means here we have to consider the object at a particular depth from Earth's surface. Just see. Okay, so this is Earth, say. Now we all assume an object at a depth d. Okay, and this is obviously the radius r. Now just look it. This is the radius r and the object is located at a depth d from Earth's surface. That means this is d. So this is simply r minus d. Okay, this is simply r minus d. That means here you can say that there are two spheres. The object of mass m is located inside the sphere of radius r and at the surface of a spherical shell of radius r minus d. Okay, you can say that the object of mass m is located inside a sphere of radius r, obviously, and at the surface of a spherical shell of, say, radius r minus d. Okay, so again, there are two spheres. Okay, and we will discuss it later that when an object is located inside a sphere, it will not experiences any force of attraction. That means inside a sphere or a spherical shell, whatever you can say, there is no force of attraction. Okay, but that means the object will not experience a force due to the sphere of radius r. Okay, there is no force of attraction due to this sphere, so it can only experience as a force of attraction due to the inner spherical shell. Okay, now first of all we have to find out the mass of the shell. Okay, now what is the radius of the shell? Radius of the inner shell, we all know its radius is r minus d. So the radius of the inner shell is simply r minus d. Now what would be the mass of the shell? If you call the mass of the shell to be m dash, then its volume is 4/3 pi r minus d whole cube. This is, and density is rho. What is rho? Rho is the mean density of Earth and it is constant. Okay, whenever we are talking about mean density, it is always constant, because previously I told that there are different densities in different places. That's why we write rho as mean density. So whenever we are talking about mean density, it is always constant. Okay, and we can write, if m is the mass of Earth, then we can write its mean density, that is 4/3 pi r cube rho, and from which we can always write rho as 3m upon 4 pi r cube. So we can put rho, the value of rho, in this expression. Okay, so 4 pi upon 3 r minus d whole cube 3m by 4 pi r cube. Okay, so m into r minus d whole cube by r cube. So this is the mass of the spherical shell. Okay, we have found the mass of the inner spherical shell is this. Okay, because in order to find out the force of attraction, it is necessary to find out the mass of the shell. Okay, now we can easily conclude what will be the force of attraction. So force of attraction between the shell and object. Okay, so if we call it F, then G. Okay, what is the mass of the cell? That is 4, oh sorry, m into r minus d whole cube by r cube into m, mass of the object by their distance. The object is located here, this, and this distance is r minus d, so r minus d whole square. Okay, so we can write it. If we simplify it, we get gmm into r minus d by r cube. Okay, gmm by r cube into r minus d. Now if we take m in LHS, so it will be f by m, and this can be written as gm by r square into r minus d upon r. Okay, so what is f by m? Acceleration due to gravity at a depth d. So you can write it gd, say, and this is simply at the surface g into 1 minus d by r. Okay, so this is the formula. Acceleration due to gravity at a depth d, gd equals to g into 1 minus d by r. Now this formula is used in order to find out the weight of an object located at the center. Okay, whenever you are asked to show that weight of an object at the center of earth is 0, at first you have to derive this relation. Okay, now we all know that if the object is, instead of d, if the object is located at a depth d, at a depth d equal to r, so if d equal to r, that means this will become d, radius is become d. Okay, so gd will be 0. Okay, so whenever you are asked to find out the weight of an object at the center of earth, you have to derive this formula. Now at center, what happened? At center, we all know that d is r, that means gd is 0. If gd is 0, then m into gd is 0. So weight of an object at the center of earth is 0. So this is how we can find out the weight of an object. Okay, so we see that acceleration due to gravity at a height h is can be written in this way, g into 1 minus 2h by r. Okay, and at a depth d, that can be written in this way, g into 1 minus d by r. Now it is a numerical question that at what depth these two acceleration due to gravities are equal. Okay, so you can set a numerical problem, that is at what depth the acceleration due to gravities are equal. So if you equal gd equal to gh, then what will be the result? G cancels, 1 cancels, so d by r, this equals to 2h by r, so from which we can easily write d equal to 2h. So at this depth, both the acceleration due to gravities are equal, and you can set a numerical question itself. Okay, so this is the depth at which both the acceleration due to gravities are equal. Okay, so in our today's class, I shall discuss about the variation of g with altitude and depth. Okay, now in my next class, I shall going to discuss the effect of Earth's rotation on g, that is the diurnal motion. Okay, and how it can affect g, and from this we can conclude that the g is not same at poles and equator, they are different. Okay, that I will do in my next class. So dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest videos. Okay, thank you.